We begin by constructing a square with side 5 units. You can easily verify this by looking at the horizontal and vertical rulers in the screen. You can see here that we have constructed a big square with side equal to a plus b. You can actually see that a equals 2 units and b equals 3 units. And this is consistent with the fact that the side of the big square measures 5 units, which is 2 plus 3. This illustration also shows that we have 4 right triangles such that the measure of one leg is A and the measure of the other leg is B. Let C be the measure of the hypotenuse of each of these congruent right triangles. Let us now have another square of the same size, and let us rearrange the 4 triangles to form 2 rectangles of sides A and B. You can actually see that in this rearrangement, A equals 2 units and B equals 3 units still. And this is consistent with the fact that the side of the big square measures 5 units still. Using the first illustration, the area of the big square, that is the square with side A plus B, is equal to the total area of the 4 congruent right triangles plus the area of the square in the middle with side C. We know that the figure in the middle is a square since it has 4 congruent sides. You might say that it could be that we only have a rhombus here, and that the tilted quadrilateral in the middle of the figure, which is a rhombus, is not necessarily a square. We will show later that this is indeed a square and not just a rhombus. The area of each triangle is equal to 1/2 AB, and the area of the small tilted square in the middle is C squared. Since the area of the big square is equal to the total area of the 4 congruent right triangles plus the area of the square in the middle with side C, it follows that the area of the big square equals 4 times 1/2 AB plus C squared. Since 4 times 1/2 is 2, this can be further simplified to 2AB plus C squared. But we know that the area of the big square with side A plus B is the quantity A plus B close quantity squared. And that quantity A plus B close quantity squared can be expanded and further simplified into A squared plus 2AB plus B squared. Since we are here dealing with the same square, it follows that the two computed areas are equal. That is, 2AB plus C squared is equal to A squared plus 2AB plus B squared. Using addition property of equality, adding negative 2AB to both sides of the equation, we now have C squared equals A squared plus B squared, which is the Pythagorean theorem. The Pythagorean theorem states that if we have a right triangle with hypotenuse C and we let the sides or legs be A and B, then the square of the hypotenuse is equal to the sum of the squares of each of the legs. C squared is equal to A squared plus B squared. Now, the area of the other square, which is of the same size, is equal to the area of the two rectangles, which is each composed of 2 triangles, plus the area of the square with side A, plus the area of the square with side B. We know that the area of the rectangle is equal to length times width. Hence, the area of the two rectangles is 2AB. And the area of the big square is 2AB plus the area of square 1, which is A squared, plus the area of square 2, which is B squared. The area equals 2AB plus A squared plus B squared. The total area equals 2AB plus A squared plus B squared. But remember that we are here talking of two congruent squares. Hence, 2AB plus C squared equals 2AB plus A squared plus B squared. Using addition property of equality, that is adding negative 2AB to both sides of the equation, we now have C squared equals A squared plus B squared. Let us now establish that the tilted quadrilateral or rhombus in the middle of the first illustration is indeed a square. We know that the corner angle here is a 90-degree angle. we let one angle of this triangle be angle 1, and since the sum of the measures of the angles of a triangle equals 180 degrees, the remaining angle is 90 degrees minus the measure of angle 1. The angle formed by side B and side C is 90 degrees minus the measure of angle 1. We let the corner of this tilted rhombus with side C be angle 3. Is angle 3 a right angle? We have 3 angles here whose sum is 180 degrees. That is 180 degrees equals measure of angle 1 plus measure of angle 3 plus 90 degrees minus the measure of angle 1. Simplifying this further, measure of angle 1 minus measure of angle 1 is 0, and we have 180 degrees equals measure of angle 3 plus 90 degrees. Using addition property of equality, that is adding negative 90 degrees to both sides of the equation, we now have the measure of angle 3 which is 90 degrees. Hence, we have a right angle here. And since we know that all the sides of this tilted quadrilateral are congruent, and each of the angles here is a right angle, then this tilted quadrilateral here is not just a rhombus, and is indeed a square, and all our calculations above hold. We were able to derive the Pythagorean theorem, which states that in a right triangle with hypotenuse C and with sides or legs A and B, the square of the hypotenuse is equal to the sum of the squares of each of the legs. That is, C squared is equal to A squared plus B squared. We may now begin our discussion of the Pythagorean triples. That is, we shall determine the integer solutions of C squared equals A squared plus B squared. The Pythagorean triple is every triple of positive integers A, B, C such that A squared plus B squared equals C squared. For starters, let us determine one Pythagorean triple. Let us do this by illustrating a triangle with sides 3 units and 4 units. Let A equals 3 units and B equals 4 units. What is the value of C? We know that C squared is equal to A squared plus B squared. Hence, C squared is equal to 3 squared plus 4 squared. 3 squared is 9 and 4 squared is 16. C squared is equal to 9 plus 16, which is equal to 25. C then is equal to the square root of 25, the positive square root of 25, which is 5 units. 3, 4, 5 then is an integer solution to A squared plus B squared equals C squared. Hence, 3, 4, 5 is a Pythagorean triple. A triple of natural numbers A, B, C is called a primitive Pythagorean triple if A squared plus B squared equals C squared and the GCD of A, B, and C is equal to 1. 3, 4, 5 is a Pythagorean triple. But so is 6, 8, 10, since 6 squared plus 8 squared equals 10 squared. 6 squared is 36 and 8 squared is 64. 36 plus 64 is equal to 100, which is 10 squared. Actually, so is 9, 12, 15. 6, 8, 10, and 9, 12, 15 are Pythagorean triples, but they are not primitive Pythagorean triples. These two are actually generated from the primitive Pythagorean triple 3, 4, 5. 3, 4, 5 is primitive since the GCD of 3, 4, 5 is 1. 2 times the whole of the Pythagorean triple 3, 4, 5 is equal to 6, 8, 10. The GCD of 6, 8, and 10 is 2. 3 times the Pythagorean triple 3, 4, 5 will give you 9, 12, 15. The GCD of 9, 12, and 15 is 3. What other Pythagorean triples generated from 3, 4, 5 can you think of? And a more important question is, how can we generate primitive Pythagorean triples? What we have here is a theorem that would help us generate other Pythagorean triples that are primitive. It says that the set of all primitive Pythagorean triples ABC with A odd and B even is the set of all triples n squared minus m squared, 2nm, and n squared plus m squared, where n and m are positive integers of opposite parity, meaning when n is even, m is odd, and when n is odd, m is even, with n greater than m and m greater than 0. And the GCD of n and m must be 1. Thus, every Pythagorean triple is of the form lambda times n squared minus m squared, lambda times 2nm, and lambda times n squared plus m squared, for some lambda greater than or equal to 1, and some n greater than m and m greater than 0. We shall derive this formula of generating Pythagorean triples, and then later on, we shall use this formula in generating Pythagorean triples. Let us recall that our Pythagorean triple satisfies the formula c squared is equal to a squared plus b squared. If we divide both sides of the equation by c squared, we shall end up with 1 equals a squared over c squared plus b squared over c squared. This can be further simplified into 1 equals a over c quantity squared plus b over c quantity squared. Now, what does this equation mean? This equation means that in the Cartesian plane xy, we have a point x which is equal to a over c and y which is equal to b over c. That is on the unit circle x squared plus y squared equals 1. Because remember, this is of the form 1 is equal to x squared plus y squared, which is the equation of a unit circle. Remember that in a unit circle with center at the origin, since the radius is 1, it satisfies the equation x squared plus y squared equals 1. And this equation is of the form x squared plus y squared equals 1, where x is a over c and y is equal to b over c. Since a, b, and c in the Pythagorean triple are all integer solutions to the Pythagorean theorem c squared is equal to a squared plus b squared, we are now sure that x here is a rational number a over c, and y is another rational number b over c. We shall make use of this, knowing that finding all the Pythagorean triples is equivalent to finding all rational points on the unit circle x squared plus y squared equals 1. Recall that we have already established this in another report on Fourier diagram. We learned there that there is a one-to-one correspondence between primitive Pythagorean triples and points on the unit circle. In this slide, in the discussion on Fourier diagram, PQ is used instead of MN. And here we have a point on the unit circle 4 over 5, 3 over 5. This shows that in relation to the Pythagorean triple 3, 4, 5, C here is equal to 5, and the numerators 4 and 3 correspond to the value of A and B. We have here the Pythagorean triple 3, 4, 5, and this shows that there is a one-to-one correspondence between primitive Pythagorean triples and points on the unit circle. In order to find all the rational points on the circle x squared plus y squared equals 1, we shall use this construction. Since we are here dealing with the unit circle, one obvious point on the circle is the point 0, 1. Now let us consider a line which intersects the circle in this point 0, 1 and some other point P. Let this be your R since later on, we shall have circles of radius bigger than 1. And so if we must generate a circle of radius r other than 1, this r here corresponds to that general radius not necessarily equal to 1. Of course, we know that this point P here is the general point xy. It could be any point on the unit circle. Since we now have here a line, we may define this line by the equation y equals mx plus b, where m is the slope and b is the y-intercept. We know that b here is equal to 1 because the intersection of that line and the y-axis is the point 0, 1. Now, what is the slope of that line? We know that the slope may be defined as rise over run. And since we have a unit circle here, from one point to another point, our rise from 0, 1 to r0 is negative 1, and our run is equal to r. Hence, m is equal to negative 1 over r. Now, this gives us the equation of this line, which is y is equal to negative 1 over r x plus 1, which may also be written as y is equal to 1 minus x over r. Let us now solve for x, and then after determining x, we now have a way of getting y, which is y is equal to 1 minus x over r. Remember that since r here is the radius of a general circle, not necessarily the unit circle, then r is not equal to 0. Hence, this could never be undefined. Now, in a unit circle, the equation is x squared plus y squared equals 1. Substituting the value of y in this equation, we now have x squared plus the quantity 1 minus x over r close quantity squared equals 1. Let us simplify this further. This here is simply the binomial expansion of the expression 1 minus x over r. Using addition property of equality, that is adding negative 1 to both sides of the equation, 1 here and this 1 on the right side of the equation would be 0. Hence, we have the equation x squared minus 2x over r plus x squared over r squared equals 0. Let us collect all the terms with coefficient x squared. Combining these two terms, we now have x squared plus r squared plus x squared all over r squared. Minus 2x over r is equal to 0. Let us now factor out x squared in this portion of our equation. So we're going to have r squared plus 1 all over r squared quantity times x squared minus 2x over r equals 0. This may be rewritten into the quantity r squared plus 1 all over r squared close quantity x squared equals 2x over r. And since we are here solving for x, knowing that x there is not equal to 0, remember that this x here cannot be equal to 0 since it's a point in the first quadrant. So P here is a point on the unit circle that is not on any of the axes. Since we know that x is not equal to 0, we may divide both sides of the equation by x. So we now have the quantity r squared plus 1 all over r squared close quantity x equals 2 over r. And dividing both sides by r squared plus 1 all over r squared to solve for x, we now have x is equal to 2 over r squared plus 1 over r squared. So we have x is equal to 2r over r squared plus 1. Now remember that y is equal to 1 minus x over r. So knowing what the value of x is, we can now have the corresponding value for y. So we know that y is equal to 1 minus x over r, and substituting the value of x here, we have y equals 1 minus the quantity 2r over r squared plus 1 all over r. Simplifying this further, we have y is equal to 1 minus 2 over the whole of r squared plus 1. And combining this into a single expression of the form a over b, we have y is equal to r squared minus 1 all over r squared plus 1. So going back, this point P here has coordinate x 2r over r squared plus 1 and y equal to r squared minus 1 all over r squared plus 1. Now we can go back to finding the formula for Pythagorean triples. Since we are here interested in finding the coordinates of a point on the circle such that that circle has a radius that is not necessarily equal to 1, we want r here to be a rational number. So let r be the rational number having integer numerator and integer denominator. Let that be P over Q. Let us copy the same derived coordinate point corresponding to xy. Noting that r this time is a rational number represented by P over Q. In some other literatures, they use m over n. Anyway, these are just but variables. The only thing that we want to show here is that r is a rational number of the form P over Q or m over n, or use any other letters that you want. For conformity to the previously stated theorem, let us use m over n. But you'll find out that in some other books related to this topic, they use P over Q. So for the x value, we have 2r over r squared plus 1. And this time, using m over n as the value of our r, we have 2m over n all over m squared plus n squared all over n squared. So simplifying that complex fraction, we have 2mn squared all over n times the quantity m squared plus n squared closed quantity. We may cancel common factors in the numerator and in the denominator. So x here, which has this value, now has the value 2mn over m squared plus n squared. This time, let us solve for the corresponding value for y. Again, noting that r is equal to m over n. So r squared minus 1 all over r squared plus 1 becomes, simplifying this portion, we have m squared minus n squared. And simplifying this portion, we have m squared plus n squared. So these two will cancel each other out, since one will be part of the numerator and the other one will be a factor in the denominator. Hence, we now have m squared minus n squared all over m squared plus n squared for the value of the y coordinate. So this is x and this is y. Now that gives us r is equal to m over n and pxy has the corresponding value 2mn over m squared plus n squared, m squared minus n squared all over m squared plus n squared. But remember that x is of the form a over b and y is of the form b over c. So this is c and this is c. Now going back to the formula a squared plus b squared equals c squared, we know that a is equal to 2mn. Since this is of the form b over c, then b is equal to m squared minus n squared. And c is the denominator. This here is the value of c. These here are the values mentioned in the previously stated theorem. That is, a is equal to n squared minus m squared. B is equal to twice mn or 2nm. And c is equal to m squared plus n squared or n squared plus m squared. Since we are here dealing with Pythagorean triple, it doesn't matter if you have it written as ABC or BAC. A squared plus B squared is equal to C squared. And B squared plus A squared is also equal to C squared. So A could be N squared minus M squared and B could be 2NM, or they may have interchanging values. And still, what you have is a Pythagorean triple. That is to say that the Pythagorean triple 3, 4, 5 may also be written as 4, 3, 5. And still, we have a Pythagorean triple. Now, let's try to generate Pythagorean triples. Specifically, we want Pythagorean triples that are primitive. And we've already talked about the theorem that will help us generate all these primitive Pythagorean triples. The set of all primitive Pythagorean triples ABC with A odd and B even is the set of all triples n squared minus m squared, 2nm, and n squared plus m squared. So we already have all of those as formulas in our Excel file. Here we have the formula for our A, which is n squared minus m squared. In some literatures, they use Q and P instead of n and m. We have here Q squared minus P squared, or that is just but actually the same as n squared minus m squared. And then, to generate B, our formula is simply to multiply m and n. Here, it says that we have to multiply n and m. So, it's twice nm, which is just but the same with twice mn. If you're using the variables pq, that's just but the same as twice pq. And to generate the third element in our Pythagorean triple, that is the value for C, the formula is n squared plus m squared. We're writing our n first before m, since in our formula it says that n is greater than m and m is greater than 0. And we want the GCD of n and m to be equal to 1. We want them to be relatively prime. Since we are only interested here in generating primitive Pythagorean triples, we shall follow the conditions set forth in this theorem. If you want to generate other Pythagorean triples that are non-primitive, then you may use this formula given. Lambda is introduced as a multiplier to each of those values for A, B, and C. So let's generate our first primitive Pythagorean triple. And I want a value for n here, which is the smallest possible integer value that n could have. Since n is greater than m, we must write 2 here, and m must be 1. One condition set forth here is that n and m must be of opposite parity, which means that if n is even, then m must be odd, or vice versa. So this follows that condition. Since we have n equals 2, m equals 1. And 2 is even and 1 is odd. By plugging in the values for n and m, we were able to generate our Pythagorean triple here. We have A equals 3, B equals 4, and C equals 5. The first primitive Pythagorean triple has just but been generated. The next possible value here for n is 3. And if your n is 3, your m must not be odd anymore because 3 is odd. We could have m equals 2 here. So with n equals 3 and m equals 2, we were able to generate our next primitive Pythagorean triple, which is 5, 12, 13. If you're going to substitute these values to a squared plus b squared equals c squared, 5 squared plus 12 squared is equal to 13 squared. 5 squared is 25, 12 squared is 144, and 13 squared is 169. 25 plus 144 is equal to 169. What do you think is our next possible value for n, and correspondingly, what shall we have for m? If you are thinking of the number 4 for n, you are correct. So let's plug in 4 here. And since we want our n and m to be of opposite parity, since n is even, n is 4, then m must be odd. So what's the possible value for m? Here we could have 3. So with n equals 4 and m equals 3, we now have this primitive Pythagorean triple. 7, 24, 25. You may verify that using your calculator. 7 squared plus 24 squared must be equal to 25 squared. Alright, so aside from the pair 4, 3, we could have another pair with 4 as one of the values for n and m. If n is equal to 4 and we want a number for m which is odd this time, we could have here 1. So with n equals 4 and m equals 1, we have the primitive Pythagorean triple 15, 8, and 17. 15 squared plus 8 squared must be equal to 17 squared. Suppose we violate the conditions set forth in our theorem. Suppose I have here 4 and I want 2 as a pair for 4. Notice that 4 and 2 are both even numbers, and so they are not of opposite parity. 12 squared plus 16 squared, is that equal to 20 squared? If your answer is that they are equal, then you are correct. So we still have here a Pythagorean triple. 12, 16, and 20 still form a Pythagorean triple. But this is not a primitive Pythagorean triple. Because for it to be a primitive Pythagorean triple, the GCD of A, B, and C must be 1. And in the case of 12, 16, and 20, the greatest common divisor for 12, 16, and 20 is 4. 12 could be divided by 4, 16 could be divided by 4, and 20 could be divided by 4. So their GCD is not 1. That's why this is not a primitive Pythagorean triple. If you want a primitive Pythagorean triple, you must strictly follow the conditions set forth in this theorem. This may actually be interpreted as lambda times 3 and then lambda times 4 and then lambda times 5, because this is generated from the primitive Pythagorean triple 3, 4, 5. What is the value of lambda in the case of 12, 16, and 20? Lambda actually is the greatest common divisor of 12, 16, and 20. As was mentioned a while ago, lambda or the GCD is equal to 4. 4 times 3 gives you 12, 4 times 4 gives you 16, and 4 times 5 gives you 20. So let me delete that from our Excel file since we only want to generate here our primitive Pythagorean triples. So the next possible value for n must be 5. And if we have 5, a possible pair for 5, a corresponding value for m is 4. With n equals 5 and m equals 4, we now have 9, 40, and 41. 9 squared plus 40 squared is equal to 41 squared. What do you think must be the next pair of n and m here? Could we still have 5 here? If your answer is yes, you are correct. So if we have 5 here, a possible pair for 5 other than 4 is, could we have 3 here? If you're going to have 3 here, since they are not of opposite parity, again, you'll have a Pythagorean triple that is not primitive. A possible partner or pair for 5 must be 2. Since 5 is odd, we want an even number for m. So now we have the Pythagorean triple 21, 20, 29. I guess that's it for the rest of the possible values of n and m. I will leave that to you as an exercise. I want you to generate some other possible primitive Pythagorean triples here with chosen values for n and m satisfying the conditions set forth in this theorem. Specifically, as your seat work, I want you to generate the first 20 primitive Pythagorean triples. Alright, let's just have an additional question. If you have 6 as the value for your n, is it possible for you to have 3 as value for m? Is this a primitive Pythagorean triple? If your answer is yes, that's a wrong answer. What do you think was violated in the theorem? Why were we not able to generate a primitive Pythagorean triple? This is still a Pythagorean triple, but obviously it's not a primitive Pythagorean triple. So the question is, what condition was not satisfied in this theorem. I hope that that helps you generate some other primitive Pythagorean triples following all of these primitive Pythagorean triples. How do we generate primitive Pythagorean triples? Another question, how do we generate a family of Pythagorean triples from a primitive Pythagorean triple? And number 3, in deciding which values for n and m must be inputted in, say, your Excel formula, what conditions must be met? Show an example and a non-example, meaning a pair of n and m that do not satisfy any of the conditions you have just set. I guess that's it. Thank you.